On the 20th of July, 1969, man set foot on the moon, 3 days of flight, a second's delay in communication. If something goes wrong, Earth is outside the window. More than half a century has passed since then. We have built orbital stations, we have landed our drones on Mars, we have photographed black holes, but no one has ever left the vicinity of Earth. Mars is waiting. It has been waiting for 50 years, and we still cannot take that step, not because we don't want to, but because we don't know how to return alive. When Neil Armstrong left his first footprint in the lunar dust, NASA engineers were already plotting routes to Mars. The year was 1970. Euphoria reigned. It seemed that the red planet was a matter for the next decade. 2 at most. Werner von Braun, architect of the lunar program, presented a detailed plan to Congress: nuclear engines, an orbital shipyard, a fleet of spacecraft, the first landing, 1982, 12 years from now. That didn't happen. It didn't happen in the 1990s either, when President Bush Sr. announced the Space Exploration Initiative. The price tag was $450 billion. Congress rejected it. This did not happen in the 2000s, when Bush Jr. promised to return Americans to the moon and then send them to Mars. The Constellation program died before it was even born. It did not happen in 2010, when Barack Obama called the mid-1930s a new horizon. We are approaching that deadline. The horizon is still as distant as ever. Every generation received a promise. Every generation watched as that promise dissolved into budget debates, technical reports, and a quiet admission. We are not ready. But it's not about politicians, it's not about money, it's not about a lack of will, it's all about distance. The moon is our closest neighbour, 384,000 kilometres. Light travels this distance in 1.3 seconds. The Apollo astronauts could talk to Houston almost in real time. If something went wrong, as it did with Apollo 13, Earth was close by. 3 days' journey home. Mars is different mathematics, different physics, a different reality. The average distance is 225 million kilometres. That is not a typo. 225 million. Depending on the position of the planets in their orbits, the figure varies from 55 million to 400 million kilometres. Let's convert this into understandable units. If you could drive a car at a speed of 100 kilometres per hour without stopping, the journey to the moon would take about 160 days. The journey to Mars would take 257 years. Light, the fastest phenomenon in the universe, takes between 3 and 22 minutes to reach Mars. Radio signals travel at the same speed. This means that if an astronaut on a Martian spacecraft says, "Houston, we have a problem," the response will arrive in 44 minutes, at best. 6 minutes of silence when the wiring is burning. 20 minutes of silence when depressurization is eating away at the air. 40 minutes of silence when someone in the crew stops breathing. The Earth will not be able to help. The Earth will not even be able to find out in time, and this is just the beginning. The distance to Mars is not just a number in an astronomy textbook. It is a sentence written by the laws of physics, and this sentence has several clauses. Article 1. Time. Modern chemical-fueled rockets can deliver a spacecraft to Mars in 6 to 9 months. This is not a weekend trip, it is a period comparable to pregnancy. Only instead of a new life at the end of the journey, there is a crew locked in a metal capsule in the middle of absolute emptiness. But getting there is only half the battle. Mars and Earth move along their orbits at different speeds. To return home along an energy-efficient trajectory, the astronauts will have to wait 500 days, almost a year and a half on the surface of a foreign planet before the window for return opens. Then another 6 to 9 months for the return journey. The total duration of the mission is about 900 days, 2.5 years away from Earth. For comparison, the longest continuous human flight in space is 437 days. Valery Polyakov's record at the Mir space station. And even then, Earth was 400 kilometres below, not 200 million kilometres. Article 2. Radiation. On Earth, we live at the bottom of an air ocean, under the dome of a magnetic field. These two shields stop almost everything that the universe sends our way. We don't think about it, just as fish don't think about water. But as soon as you climb higher, the protection disappears. The International Space Station flies at an altitude of 400 kilometres. Even there, astronauts receive a dose of radiation 200 to 300 times higher than the Earth's norm. In 6 months on the ISS, a person accumulates about 80 millisieverts. This is acceptable. It's taken into account in the calculations. Mars is a different story. Beyond the Earth's magnetosphere lies the territory of galactic cosmic rays. This is no ordinary radiation. These are the nuclei of heavy elements, iron, titanium, silicon, accelerated by supernova explosions to near-light speeds. They have been travelling through space for millions of years, and when one such ion passes through a living cell, it leaves a trail of destruction behind it. A conventional X-ray damages DNA at a single point. The cell can usually repair this damage. A heavy ion knocks out pieces of genetic code along the entire length of the molecule. This type of damage is called cluster damage. The cell does not know how to repair this. It either dies or mutates. During the flight to Mars and back, an astronaut will receive between 1,000 and 1,200 millisieverts. This is twice NASA's current lifetime limit. 600 millisieverts is the ceiling. After that, the cosmonaut is grounded for good. One flight to Mars, and you've exceeded the limit twice. Is it possible to protect yourself? Theoretically, yes. Practically, almost no. The aluminium walls of the spacecraft, the same as those on the ISS, not only fail to stop heavy ions, they make things worse. When a particle collides with metal, it generates a shower of secondary radiation. Neutrons, protons, nuclear fragments. All of this flies inside the spacecraft. To effectively block galactic rays, several meters of water or special polymers would be required. The mass of such a shield would make the spacecraft unliftable for any existing rocket. There are ideas involving active magnetic shielding, an artificial field around the spacecraft like Earth's, but this technology exists only on paper and in laboratories. While we fly to Mars on chemical rockets, we fly naked. Article 3. The body. The human body is the product of 4 billion years of evolution on a planet with a specific gravitational pull. Every bone, every vessel, every organ is designed to function under Earth's gravity. Remove gravity, and the system begins to break down. Bones. In weightlessness, the skeleton does not need to support the body's weight. The brain receives a signal. Calcium is no longer needed in such quantities. Resorption begins. The bones literally dissolve from the inside. The rate of loss is between 1 and 1.5% of mass per month. During a 9-month flight, an astronaut can lose up to 15% of bone tissue in their lower limbs. This is the level of severe osteoporosis. A fracture from an awkward movement becomes a real threat. Muscles deteriorate even faster. Postural muscles, which keep us upright, suffer particularly badly. On Earth, they work every second we're awake. In weightlessness, they have nothing to do. Atrophy begins in the first days of flight. Astronauts on the ISS train for 2 hours every day to slow down the deterioration. Slow down, not stop. But all this is just dry data from medical reports. Let's translate it into reality. Imagine what happens to a person day after day, month after month on the way to Mars, the first week. The body does not yet understand what has happened. Fluid, which on Earth accumulates in the legs under the influence of gravity, begins to redistribute itself. It rises upwards towards the head. The face swells. There is a feeling of constant congestion, a stuffy nose, pressure in the temples. Astronauts call this moon face. The first month, your vestibular system goes haywire. On Earth, it uses gravity as a reference point. Here there is no reference point. Nausea, dizziness, disorientation. For some, it goes away in a week. For others, it lasts for months. Third month. The bones began to lose mass in the early days, but now the process is becoming measurable. Tests show elevated calcium in the blood. The skeleton is releasing minerals. The kidneys are working overtime to remove the excess. The risk of kidney stones is increasing. A 2024 study from University College London stated outright that prolonged exposure to cosmic radiation and microgravity poses serious risks to the kidneys. The longer the flight, the higher the likelihood of failure. 4th month, vision begins to change. This is SANS syndrome, space neuroocular syndrome. Fluid accumulated in the head puts pressure on the eyeballs and optic nerves. The eye literally changes shape. It becomes flatter. Vision shifts towards long-sightedness. 70% of astronauts who have spent more than 6 months on the ISS have shown signs of this syndrome. For some, The changes are irreversible. Think about it. You haven't even reached Mars yet, and your eyes are already different from the ones you started with. The 5th month. The heart, which no longer needs to pump blood against gravity, begins to slacken. It changes shape, becoming more spherical. Its rhythm slows down. The volume of blood pumped decreases. When an astronaut finally steps onto the surface of Mars, with its 38% of Earth's gravity, the heart may not be able to cope with even this load. This condition is called orthostatic instability. Simply put, you are unable to stand. Blood drains from the brain, your vision darkens, and your legs buckle. The first people on Mars may not be able to take a single step after landing. 6th month. The ship is approaching its destination. But the people inside it are no longer the same people who left Earth. Their bones have weakened, their muscles have atrophied, their vision has changed, their hearts are working in a low-impact mode. Now add something that wasn't on the ISS, deep space radiation. Every day of flight, heavy ions pass through the astronaut's body. Each leaves a microscopic scar in the DNA. The body repairs most of this damage as best it can. Some remains, it accumulates, it waits for its moment. Cosmonauts on the ISS sometimes see flashes even with their eyes closed, white streaks at the edge of their vision. These are heavy particles passing through the retina, stimulating the optic nerves. Beautiful and frightening. Each flash is an ion piercing the brain. Animal studies have shown that chronic exposure to heavy ions damages neural connections, memory deteriorates, reaction speed declines. The ability to make decisions in stressful situations, precisely what is most needed in an accident, is reduced. We send the best of the best to Mars, and the flight itself makes them weaker. This is not theory. This is not a horror story. This is physics and biology working against us. The body is only part of the equation. There is also the mind. In 2010, 6 volunteers entered an airtight complex on the grounds of the Institute of Biomedical Problems in Moscow. They did not fly anywhere. They simply closed the door behind them and did not open it for 520 days. The experiment was called Mars 500. It was the longest interplanetary flight simulation in history. 3 Russians, 1 Frenchman, 1 Italian, and 1 Chinese. A confined space, limited resources, an artificial delay in communication with the control center, up to 25 minutes one way. Everything was just like in a real flight, except for one thing. Moscow was behind the wall. In the event of a real disaster, a fire, depressurization, a medical emergency, the door could be opened. There is no door on the way to Mars. The results of the experiment were published in scientific journals. 4 of the 6 participants experienced severe sleep disturbances. 1 crew member spent most of the mission in a state of chronic sleep deprivation, which affected his cognitive functions. The researchers recorded the stages of psychological adaptation, stability at the beginning, disorganization in the middle, and attempts at reorganization towards the end. But something else was even more alarming. As the communication delay increased, the crew became more and more independent and more closed off. They shared their problems with Earth less often. They followed recommendations less often. Gradually, psychological isolation formed, not only from the outside world, but also from those who were trying to help them. In psychological terms, this is called crew autonomization. In plain language, the team stops listening to Houston. Now imagine this in real flight. The Earth is not behind a wall, the Earth is 200 million kilometers away, and it turns into a dot. There is a phenomenon that astronauts are reluctant to talk about. It is called the overview effect. Those who have seen Earth from space describe a transformative experience, an awareness of the planet's fragility, the unity of humanity, and their place in the universe. This works as long as Earth fills the sky outside the porthole, blue, alive, close. But there is also a downside. Researchers call it the Earth disconnect phenomenon. When your home planet becomes just another bright spot among thousands of other stars, something changes in your psyche. Existential anxiety, the feeling that the connection to home has not just weakened but been severed. Some experts suggest that this can trigger depression, depersonalization, and loss of motivation. No one in history has truly experienced this. The Apollo astronauts saw Earth as small, but their mission lasted days, not years. The ISS crews see it as enormous every 90 minutes. The first Mars astronauts will be pioneers not only in a geographical sense, they will be test subjects in an experiment that cannot be conducted on Earth. And we haven't even mentioned the technology yet. Humans need air, water, food, heat. On the ISS, all of this is delivered by cargo ships every few months. If something breaks, spare parts can be sent. Nothing can be sent on the way to Mars. Everything needed to survive 2.5 years must be on board from the start, or produced on site. Modern life support systems on the ISS recover about 90% of water. It sounds impressive, until you calculate the losses. 10% per month, over 30 months of the mission, this is a disaster. Mars requires efficiency close to 100%. Such technology does not yet exist in a ready-made form. The European Space Agency is working on the Melissa project, a closed ecosystem with algae and bacteria capable of converting waste into oxygen and food. On paper, it looks elegant. In practice, it will take decades to get it ready. There has been progress. In 2021, the MOXIE device installed on the Perseverance rover began operating on Mars. It obtained oxygen from the Martian atmosphere for the first time by splitting carbon dioxide molecules. Proof of concept. But there is a huge gap between a tiny experiment and an industrial installation capable of supplying a crew. And then there's the equipment breaking down. That's just how it is, and decades of running the ISS have shown that. Something's always going wrong on the station: pumps, filters, electronics. The crew fixes it. Earth sends spare parts. Spare parts cannot be sent to Mars. NASA engineers say that critical systems need to be tripled, 3 pumps instead of 1, 3 air purification units, 3 sets of electronics. The weight of the spacecraft increases, the cost increases, and so we come to the final barrier, the most earthly of all: money. How much would it cost to send a person to Mars? Estimates vary from $100 to $500 billion. The range is huge, because no one has really calculated it. This is not an estimate, it is guesswork based on orders of magnitude. For comparison, the Apollo program cost about $25 billion in 1960s prices. In today's money, that's about $190 billion. But Apollo means 6 successful landings on the Moon, which is 1,000 times closer than Mars. The International Space Station cost $150 billion. It took 20 years to build, and it hangs in low orbit, which can be reached in 6 hours. Mars is Apollo and the ISS combined. In terms of complexity, timing, and cost, it may be more expensive than both projects combined. No government in history has ever allocated such funds to a single space mission. Political cycles last 4 years, 8 at most. The Mars program will take 20 to 30 years of development before the first launch. Every new president, every new Congress, every new budget crisis is a threat. The Artemis program, which aims to return Americans to the Moon, is seen as a training ground. A lunar base, a long-term presence, testing technologies. The logic is clear. Before jumping across a chasm, learn to jump across a stream. But even Artemis is stalling. Deadlines are being pushed back, budgets are ballooning. Each SLS rocket launch costs around $4 billion, and it's a one-time use rocket. There is hope for the private sector. SpaceX is developing Starship, a fully reusable system that could theoretically reduce the cost of delivering cargo into orbit by a factor of 10. Elon Musk talks about a ticket to Mars for £100,000 in the distant future. Engineers are scratching their heads. As usual, the reality lies somewhere in between. But even if Starship works, even if the cost of launch falls, there remains radiation, physical degradation, the psychology of confined space, and autonomous life support systems. None of these problems can be solved with a cheaper rocket. So we have come to the answer to the question we started with. Why haven't we flown to Mars yet? Not because politicians are cowardly, not because scientists are lazy, not because humanity has lost interest in the stars, because Mars is not the Moon. It is not the next step on a familiar staircase. It is a leap across an abyss, the bottom of which we're only beginning to discern. A distance of 200 million kilometers is not an abstract figure. It is 9 months of flight, during which the body deteriorates, the mind withdraws into itself, and Earth becomes a memory. It is a year and a half on a foreign planet, where every breakdown could be the last. It is another 9 months back, if you manage to take off. We don't rush, we calculate, and until the equation balances out. But here's what's important to understand. When John F. Kennedy promised in 1961 to land on the moon before the end of the decade, the technology to do so did not exist. The Saturn V rocket had not yet been built. The lunar module had not yet been designed. The spacesuits for walking on the moon had not yet been sewn. There was nothing but a goal and determination. 8 years later, Armstrong left his mark on the moon. Technologies are created when they are needed. Barriers fall when they are pushed hard enough. Everything we list today as insurmountable obstacles, radiation, physiology, psychology, money, are challenges. Difficult ones, but solvable ones. Perhaps the solution will be a nuclear propulsion system that will reduce the flight time to 3 or 4 months. Perhaps artificial gravity on a rotating spacecraft. Perhaps gene therapy that makes cells resistant to radiation. Perhaps something we cannot yet imagine, just as engineers in the 1950s could not imagine modern computers. We do not know when this will happen. Perhaps in the 1930s. Perhaps in the 1940s. Perhaps another generation will grow up on promises that will not come true in their lifetime. But one day, a human footprint will appear on the red sand, not because it is easy, but because it is in our nature. We left Africa without knowing what lay beyond the horizon. We crossed oceans in wooden shells. We rose into the sky in structures made of fabric and wire. Each time someone said, "It's impossible, it's madness, it's suicide." Each time someone went first. Space is not hostile, it is indifferent. It does not care whether we get there or not. It is our choice, our task, our story. And it hasn't been written yet.